my huge pleasure to introduce my colleague at the Open University, Dr. Amel Bennaceur, who's a senior lecturer in computing in the School of Computing and Communications. She's also director of research of computing at the OU as well, so it keeps her very busy. She's a computing engineer and also a software engineer, and is very interested in building stuff and making it work, but also interested in its foundations and what makes it work as well. So we're delighted to have her here to give a presentation, intriguingly entitled "The Road to Collaboration is Paved with Goals." So Amel, I'll hand over to you, and I guess people can ask questions at the end, I think is the normal practice, but they can also insert comments in the chat, which we will try and assemble and ask in some sort of sensible order towards the end.
Yes. Thank you. Thank you, Bashar, for the introduction. Just to be sure, can you see my slides now? Okay, so thanks, Bashar, for the introduction. Thanks, Radu, for the invitation. And thank you everyone for being here today. So I will be presenting our work around collaboration and how Go can support it. So the main premise of this talk is that nothing worthwhile can be achieved in isolation, and probably a lot of us realize it as well now. But whether it be people or robot or software, a lot can be achieved by working together. So when these entities work together, then they can achieve more. But while people have figured out how to work together and to collaborate successfully, more or less, the idea is how to enable autonomous agents to work together, reason, and achieve goals by collaborating either with other autonomous agents or with humans. So, and that talk is exploring how we can reason about the goal and enable those autonomous agents to collaborate. So first, to start, what do we mean by collaboration? And what's its relationship with autonomy? So to do that, I'll kind of present it around like a matrix around two areas. So the first one is whether we consider systems individually or as an ensemble, as a group of systems that need to work together. And the second dimension is their level of behavior or cognitive behavior. So the first and simplest of systems are reflexive, which means they take inputs that produce outputs. So that kind of produces a behavior that is automatic for some system if they act individually, or that is distributed, such as like a client server. And the main idea is just input, output. Then you take it to another level, which is you, of course, consider input, output, but there is also an internal state. So, and that kind of the behavior doesn't depend only on the input, but also depends on that internal state. And that produces an adaptive system when it's an individual or a connected system, where connected ensembles. So where multiple systems have that internal state and react to their input. But going even one step further is systems that have an internal state that react to input output, but also plan to achieve other goals. And that produces like an autonomous system when it's an individual one, or collaboration between systems. So the idea of collaboration here, what we mean is reasoning about a group or an ensemble of systems to achieve goals. So that kind of involved analysis and planning. And those ensemble can be very different in nature. So they can be, just cyber. So that take, serverless or services on the cloud, etc. They can be physical. So I put here food, which is as a tangible ingredient, a resource, or they can be people. So they can be cyber, physical, or social, or actually any combination of those. So you can have also robots, which are physical, or you can have a person interacting with software, so socio-technical, or you can have also robot and human collaborations. But the main point is it's not enough just to put them together. They need a goal to achieve. So and in this talk is about how to represent and reason about those goals, and then how to achieve those goals. And I'll be presenting that around those kind of 4 examples. So I'll take you on a journey starting from the first case where we take a goal, and from that we go to a collaboration between robots, and we apply it in security. That kind of is collaborative security. In the second example, it's not only goals that drive collaboration, but also how the collaboration can contribute to understanding the goals. So rather than going a top down, we go bottom up, and we take as an example recipe recommendation, so in a very resource-oriented, tangible domain. We move then to the user and interaction with the user, so a socio-technical system, and we see how in e-voting example, we can revise the software to enable that collaboration with the user, a more meaningful collaboration with users. And finally, I'll talk about our ongoing work in the task resilience node, looking at group identity and how to achieve collaboration between groups of humans and robots in an emergency scenario. So first, let's go to collaborative security, and let's start with an example. So the first example, you see a video, and that's the idea here is I forget my phone.
Amel, you forgot your phone.
So what the robot does is it tries to call me first, and it does. I don't come back. So the idea is to have another robot working with the first one, the humanoid, so they can achieve the goal of protecting the phone by actually hiding it. Okay. So the idea here is we have 2 goals, that's of protecting the phone from theft, and another secondary goal, which is keeping the room accessible, so not locking the room. We have multiple robot and software, so we have a lock that can lock the room, we have a humanoid robot now, and we have the vacuum cleaner that actually doesn't do vacuum cleaning, which is create. And the idea, what we try to achieve through that is how to make use of those devices to achieve the goals. So the first thing is, how do we represent the goals? And one of the things is, so we use, for example, we used chaos. So beginning with, the high level requirement is, we want to avoid phone theft, and we want the room to remain accessible. And one way of doing it is we can refine it to a set of other goals. So we can, for example, lock the room once the user leave, and that assumes that locking the room make it safe. So that instance is that refinement will satisfy avoiding from theft, but will hurt will be an obstacle to keeping the room accessible. Another way of doing it is to call the user. So once the user leaves, then we call it, and that assumes that the user can hear us and they can come back when they hear us. So the last one is once the user leaves, then eventually we can put the phone into a safe place, and that's the goal that we're trying to achieve. And for each of those goals, a further refinement is what kind of features and what kind of we want to either be available or want to maximize. So for example, for calling the user, we need something like text to speech. We want the ability to call actually the user. And for moving the phone from one location to another, then we need to recognize that the phone is there. We need motion. We want to maximize the speed at which we hide it. So that kind of in chaos. So the idea is we want, for example, to take the third option, which is moving the phone into a safe place. And to do that, we'll start first by considering the features. So we take each of the devices. Here we have the human robot and the vacuum cleaner, and each of them can be represented using a feature model. And that specifies not only which features are available, but also dependencies between features. So for example, the motion feature here require the use of sonar. So if you select motion, then it means also you need to select the sonar. So taking those features as motion and object recognition, and also considering that we want to maximize the speed at which the phone is moved, then we can formalize that as a constraint optimization problem and select the feature in each of the robots so that we have the features that require us to to satisfy the goal. So the aim of that is not only kind of seeing which component we can use, but also it simplifies the behavior. So for example, that's already a simplified behavior of now, but that kind of, for example, you need to connect, you need to stand up, move, locate object, pick object, or drop them. You can also have the ability to, say text. So the idea is once we select specific features, then we can project the behavior and then simplify the behavior, which actually help us in the next step, which is how do we coordinate the behavior of the two robots. And to coordinate the behavior, we have an LTL formula. So we want to move the phone from one location to a safe location. And the idea is to synthesize a controller or synthesize a third system that coordinate the actions of the two robots. So there are multiple ways that you can do synthesis. A kind of an easy way to explain it is by exploring all the states and ensuring that the trace, whatever action each robot take, you can still reach a location where that property is verified. So the idea is once you put those three behavior together, then you can satisfy the property. So, and that's what, so if we want to formalize it and have a bigger, put the whole kind of process together. So we have a set of goals that we refine into a kind of a hierarchical model we have a set of components with their capabilities, we have an environment, and the idea is that each component by itself cannot satisfy the goal. And so, you know, the now or the humanoid robot by itself cannot hide the phone. The vacuum cleaner by itself cannot hide the phone. Actually, even putting them together, if you put the two robots in the same room, it doesn't satisfy the goal. So what we really need is to find a subset of those components and synthesize a coordinator that a mediator or M that coordinate the behavior to satisfy the goal. And that's what we're trying to do, is like finding a subset of components and doing the coordination to achieve the goal. But even with that, you know, you have sometimes failure. But there are also other things. So unless there is a quick question now, moving to the second bit. Okay, moving to the second one. And so for those who, it is the afternoon, we're going to talk about, you know, brownies. So assume you want to make a recipe, you want to make a brownie. So you have a set of resources. So, and the idea, the first one where you are driven by resources is you start, I want to make a brownie, and then check which ingredients you have. And that selection is what you need for achieving, you know, your recipe. The second point, it might be that you don't have one of the ingredients for achieving it. So, and here, but you have some knowledge about, you know, substitutions. So you may not have, you know, almond flour, but you have other flours. And that kind of also depends on the user and their preferences. So, but based on that knowledge and the fact that you want to make a brownie, then you select the ingredients that go with your recipe. However, if some kind of critical ingredient, say you don't have chocolate, so the idea is, you know, you will need to revise your goal. So you can make, you know, a blondie using the resources available, which is like, you know, the flour, the butter, other things, or you can make, I don't know, an orange cake. So the idea is here, depending on the resources you have, then you may revise the goals that you want to achieve. So a little bit more formally, more abstractly. So in the first case, and that's kind of the usual case, you have a goal, you have a set of resources, and the main idea is to seek a subset of resources to achieve your goals. And if you find it, perfect. So that's what is often done when you do a goal-driven composition. So identifying which resources are there to satisfy your goal. The second step is you still have the same, you start with the goal and resources, but assume you can't find like the set of resources to achieve your goal. So you may have a knowledge-based and a matching function that specify substitutions. So then the idea is what is the subset of the resources that, you know, is similar enough to a subset that will achieve the goal. And that kind of similarity is, for example, you know, maximizing the matching function. So that's what we did. You know, you pick, rather than the original recipe with the first you know, flour, you do substitute and you pick another resource. And that kind of formulation, then it can be a constraint optimization problem. And, you know, the solution is your subset of resources. the third one is, there isn't a substitution that is satisfactory. So what we need here to do is to move from not only the goal, but we want to find, among all achievable goals. So the goals that, considering the resources, you are able to satisfy, which one is similar enough to the original goal. So searching in the space of all possible goals, the subset that will be even like similar to your goal. And that similarity is application or domain specific. So in the case, for example, of the recipe recommendation, the similarity between, the original goal and all achievable goals is based on, the common ingredient in one recipe. So two recipes are similar if they share a higher number of ingredients together. So that kind of thing help us navigate the space of all possible goals. So putting it together, the first thing is to go, like, rather than always going from goals to, components, you use also the resources to drive your composition. So you start with a set of goal, resources, and the matching function. And if you cannot find a combination of possible resources to satisfy your goal, then you go to substitution. So that will produce a list of resources, but also substitute. So you have a degradation of your goal achievement, but you're still driven by your initial goals. So, but then there is the third step, which is, you need to review your goals in order to make a best use of the resources. So in this case, you need to adapt the goals or change them based on, on your domain. And that kind of close the loop around, going from goal to resources and vice versa. But that also require a kind of an input from the user towards what goal they want to achieve. So I can stop for a second to see if there is any question right now. Okay. So moving to a more to a more socio-technical area where we consider also the user as part of the system. Let me give you an example of an e-voting case. So in this case, we considered, or we get inspired by a case of election fraud in Kentucky. So they used a software, but also kind of that uses an interactive interface for e-voting. So, and in this case, the voter is supposed to, identify themselves by entering their ID and personal password, then select a candidate, vote for this candidate or go back and change the selection. And then by the end, they need to confirm their vote or change the vote and go back and select another candidate. So, but the issue was that a lot of voters assume that once they casted the vote, then they finish the interaction and they leave the booth. What happens is that, once the voter, without confirming, leaves, then there have been corrupt election officials that enter and then change the vote. So there might be multiple ways of tackling that. You may, verify the officials, make sure that they are not corrupt. You can, stop the voter from leaving unless they confirm their vote, etc. But as software engineers, we want to, see how to revise the software to prevent failure, even if the user doesn't behave as expected. So here the goal is to avoid vote flipping. So you want to avoid users from changing the vote of the main voter. And the ensembles have, the voting machine, and especially the software here, but also, you have the voter and the election official. So the goal then is, how to go first from, avoid vote flipping into a more, software related requirement or goal. So here there might be multiple ways you can specify it. You can specify that, once the voter confirm their vote, they cannot, anyone else cannot select it in the session. You can see that the person that confirmed the vote cannot leave the session, or in every session the voter chooses the candidate and confirm the vote. But that kind of put, again, pressure on the user. So the other thing that can be kind of implemented, and that's the one we went for, is the only action that can, from the software perspective, can distinguishes a voter from, an election official is the password. So focusing on that action, and ensuring that never, when a candidate, like when the voter enter their password, then the election official cannot select another candidate, which can be kind of formulated using always, once the voter put the password, then always the election official will not select or press the selection or change the selection of the candidate. So based on that, understanding what was the assumed voter behavior. So the assumption was that the voter first enters, put their password, select or go back, vote or go back, confirm, and then exit. But those two actions, the enter and exit, are not even observable by the software. So it's not only that the software cannot control them, but they cannot distinguish between who enters and who exits. So the only way that the software can distinguish who enters is through the password. So, and by forcing or assuming that the voter will follow that kind of behavior, then it may lead to failure. So the first thing is to assume that the voter can behave in any order. So they enter, they can have the password, they can do any number of action, and then can exit. And at the same time, you have also the voting official that can do the same, except that, unlike the voter, they cannot have a password. So, and for our reasoning, we would just, to distinguish between the two, we will prefix them with like voter or election official. So the idea here is then to put them in parallel and see, once they are put in parallel, whether there is this action that property can be achieved. So one of the things is, once they are put, always kind of the behavior of the system is composed, then we can see a trace where, for example, here, where you reach those red states where this property is actually not verified. So for example, here the voter enters, put the password, selects, and then exit, and then you have the election officials that enters and then either select or vote and go back. So that kind of violates that property. And to correct it, and that kind of considering that example, how do we correct it? One of the main option is to use, for example, supervisory control or synthesis. However, because of the enter and exit functions are not observable, and you cannot change so the supervisory control can only stop some actions from happening. They cannot change the order of the actions. So one of the methods to deal with that kind of changing the order of actions and not only stopping some action from happening is to first abstract and then synthesize. What does that mean? So what we did is, like, you assume, a behavior such as, you select, you vote, you go back, you confirm. That's what you want to expect. And you kind of remove or kind of get away the password, which is the action that distinguishes the good from the bad voter. So from there, considering the property, and then apply synthesis on the abstract behavior. And that will allow us to move actions or change the order of the action. So we end up with multiple ways of ensuring that the property will be verified. So, for example, in the first proposition is you do the password first, and then you vote and you confirm, but you cannot go back. Another way is to, you can go back, select, vote, but once you enter the password, you can only confirm. Or the third version, which is, you can go back and confirm, and the password is the last step to reach, the end. So, and you may have noticed that for those of you, for example, who do a lot of online shopping, so usually the behavior is following those two last proposition, where you enter the password at the last state. So people can change, revise their analysis, but it's really the last one where you have the authentication. So it kind of extracted also a best practice. So it's kind of in line with, like, the revised software behavior or software specification is in line with best practices. So summing up, the idea is to, because users are part of the systems and they are often considered as the weakest link, so we need to first kind of make sure that their obligations are made explicit, and that that you don't need to put more obligation on the users than it's absolutely necessary. But once you relax those obligations, identifying a failure scenario and revising the specification of the software based on that kind of counterexample. And the revision is through two different steps: abstracting and then synthesizing, so that it kind of also include changes in the order in which actions are performed. And then it can fail if there is no modification that can be found, or you get a specification that will keep the goals satisfied even if the users doesn't kind of completely comply with their expectation or their obligations. So that kind of considering one user at a time. And the last case study, and that's the case we are considering in Reason, and that kind of achieving cooperation between one system or robot with a group of users. So as an example, we consider emergency situation, and there there is a lot of case studies and example of drones, robots working with what we call first responders, so working with the police, the firemen to improve emergency response. But what we are actually more interested in is how the general public, the bystander, can help into that kind of emergency response. And the idea is that in a lot of situations, that those people who are present in the beginning can contribute, save life, except that they don't always know how to do it. So the idea is, can autonomous system help in coordinating those bystanders, which we call zero responders, in opposition with the first responders, so the firemen, the police, the other kind of professionals, and also maybe kind of facilitating the coordination between those zero and first responders. So here I'm going to more focus on the human and zero responder. So the idea is you want at some point, for example, in an evacuation scenario, say, we want to maximize the number of evacuations, but we also want to maximize the participation of zero responders. And in this case, the ensembles are not made only of like one robot and the victim, but you have also groups. So you have a group of zero responders, you have a group of first responders. So far, the way we have been reasoning about humans is by considering their action, like observable actions. So, I showed it also in the previous example of the e-voting. A user perform or carry out a series of actions. So it can be kind of, those series of actions can be modeled using an automaton. But there is uncertainty around how these actions perform. So you have also a lot of another category of methods where it associates probabilities to the actions that the user carries out. So both of them focus on, that kind of behaviorist view. We focus on how humans behave as, observable actions. There is a kind of work as well around a more of an ontological view, where, for example, the work at CMU around opportunities, willingness, and capabilities. And that means like understanding the domain a priori and trying to relate some data into, there is an opportunity for the human to, intervene. Do they have, are they willing also through those indication, and what capability they have. But it also assumes, design time and still a behavior focused way of looking at humans. So, and that's the way usually when we design software, we look at, we reason about human the same way as we reason about software. So as a series of actions. So, and that's where, software engineering is not enough. So we're looking outside our domain and in more specifically into social psychology and building on social identity theory. So what it says is that during an emergency, there is a sense of common fate that leads people to build a shared identity, through which they actually help each other and cooperate toward common goals. So, and that kind of coming together and shared identity is what enforces cooperation. But at the same time, not every person shares this social identity. So you will also have signs although not the majority, but you have certain people who will adopt more individualistic pro-self behavior. However, it also says that, you know, when members of a group behave differently from, you know, that social identity, then that kind of transgression produces a payoff loss. So in a group member either is anxious because they are deviating from the group behavior, or actually, you know, it's harmful also to the group because it kind of emphasizes that lack of group cohesion. So, and through that kind of knowledge around human dynamics and behavior, the idea is, you know, how to enable an autonomous system to reason about and leverage that group dynamic, that identity, to achieve goals. So in the emergency scenario, the first one, in the emergency scenario, that kind of social identity is actually a psychological state, so that cannot be observed directly. So there is no sensor that will tell us whether there is a social identity or not. But there are, you know, markers as like indirect variables that show that this social identity is taking place, and those markers can be, you know, proximity or moving in the same direction. They can also be language. So you can hear the survivor saying things, putting references to we, us, together, everybody. So, you know, somebody can say it would be best for us to not to go, or so there are those references to, you know, a group. There are also references that kind of show that there is a bond or social interaction. What do I do now? There are also kind of shared emotion or kind of support, something like we have to think about each other, or other things. So although there is no direct way of observing it, there are kind of markers that we can reason about in language and kind of to understand that social identity. So from there, you know, for example, in terms of goals, if we want to achieve evacuation, what would be then, how do we find that goal for the autonomous system? And that thing can be kind of refined into, you know, maximizing the number of evacuation, or maximizing the social identity, so that, you know, there is no payoff loss into, you know, deviating from the group expectation. And one of the assumptions for that domain is that, you know, bystanders or zero responders seek to maximize their group belonging. And those ideas are coming from the social cycle, the social identity theory in emergency scenarios. So once we have that, once we have those goals, that's maximizing social identity and maximizing the number of evaluation, and considering those agents, the robot, the zero responders, then we can formalize it as a game theoretic model and try to find the best strategy to maximize the number of evacuation as well as maximize social identity. So one of the things is each time the zero responders will behave according to the social identity, they will receive a positive payoff, and if not, they will receive a kind of payoff loss. And the idea is, by solving it as a game theoretic model, then the best strategy will be kind of elicited for the robot. So what we did is to, you know, for example, train a model based on past interactions in emergencies, what people say in emergencies so that we can predict whether a person, so at runtime, predicting whether a person will be adopting a pro-self or a group identity, social identity during the emergency. And from that, build a model that allows the robot to see how this person is likely to behave. And based on that, kind of solve that game to elicit the winning strategy in terms of whether the robot should ask help from that person or should move to the other person, and that kind of the winning strategy. So that kind of puts into kind of count how you can not only reason about a user at a time, but reason about groups of users. So, and I kind of leave those kind of 4 examples, going from just goals and collaborative robots into a robot collaborating with groups of users. So closing the loop, we've seen how you can reason about goals and to enable those devices entities or ensembles to work together. One thing that's kind of alluded to in the second example is whether those ensembles can also reflect or evaluate the goal, change them. So in the second example, we could see that if you cannot achieve one goal, then you can create another. So in a more general way, how do we evaluate different goals and create new goals rather than only kind of only between brackets planning to achieve the goal. So that's the next frontier, was like going from also collaboration to a reflection on the collaboration and on goals. And thank you. That kind of finishes my.
Thank you very much, Amel. That was really great. A fascinating tour around the notion of collaboration and how goals can contribute for different types of collaboration in different ways, but still have a unifying framework for thinking about it in this way. So there is some time for questions. If people would like to raise their hands and ask the questions, now is your opportunity. I see Giannina and then Jinwei. So.
Hello, guys. Good afternoon. Very nice. I'd say, how can I say, a digest of this work was really put together in a lot of work in a very nice compilation. Well done, Amel.
Thank you.
I was just a bit, I was just wondering here that you have the behavior related to the goals, but I couldn't see clearly how do you make the connection between the behavior models and the goal, and also how do you represent let's say, because I mean this robotic world, they have so many variables that have to consider. So how expressive your models can be, like considering either contextual variables or even like options that relates to the behaviors themselves. Yeah, these are the basic 2 questions that I would have. But anyway, thank you very much. And once again, congratulations for a very nice presentation.
Yeah, okay. Thank you, Janina. So to go back to your first question, which is how to relate the goals representation to the behavior of individual components, like for example, the robots. So the first thing is we start with them completely separate. So we model for example, the robot behavior separate from the goals. What is interesting is about like composing them and understanding that even through the composition, how you add, basically, we add a third system, which is the coordinator or the controller, that will, which is a kind of an additional entity that will do the coordination to support the goal. So it's actually synthesizing or adding those, the controller. So the controller cannot do anything by themselves. They cannot create action. So it is only about kind of somehow calling each robot at the right time. So ensuring that that kind of coordination of behavior to satisfy the goal. So there is one assumption though, that what we call like the vocabularies, that you can, that kind of mediator and third entity can talk to all of them. And that kind of, we have to reason about, you know, how do you convert, how do you understand it and everything. And there is a kind of some assumption about the knowledge and the conversion between actions. Regarding the second question, and that's kind of the hint I was giving with the robot falling, is it's an abstraction. So there are things where, you know, we call operations such as, you know, moving the arm. So when we move the arm, there is, for example, if we call it at a high speed, then it will kind of make the robot lose their balance and fall. So that kind of controlling as well, like, you know, for example, the speed, at the level of abstraction in which we operate, so at an automata, we don't consider. But if we are doing like cyber physical system, that kind of requires that kind of combination of controls, as in, you know, that kind of speed of the arm, which we took a bit aside to kind of make the problem more tractable. But they are actually relevant parameters. It's just that once you go into those hybrid models, it becomes untractable. And there are also kind of contextual information that still don't address, but there might be addressed sometime, is that, for example, the physical space as in the location of everything. And there's some work, for example, by Liliana Pasquale and all kind of modeling that physical space. But for the moment, we don't reason about that. So yes, there is a lot of things that we left to be able to reason in a tractable way.
Thank you,
That's
Amel.
very nice.
Thank
Oh,
you.
sorry, Bashar, please go ahead.
Yeah, I was just going to say that in the interest of time, maybe we can have brief questions and brief answers. There's a couple of questions. So Jinwei Fang is the next online.
Yeah, hi. Thank you for Amel. Yeah, see, the example you gave kind of requires the quantification of many abstract variables. So how did you do that? Because that's sometimes I find it's quite challenging. One is in contextual or very abstract variables. How did you quantify them?
So I don't know which example you were referring to.
Right, the second one, resources, for example.
Yeah.
So, yeah.
So the resource, in the resource case, we actually, if you could see, we removed the reasoning about behavior and like the three other examples, so that we can focus on those kind of goal revision. And that's actually the thing where goals are really important, because they help you focus on what help you to achieve those goals. So any information, like for example, in that case, we want to, reduce food waste, or make the most of use of resources. We don't care about the process, so we could the process of combining the ingredient of the resources, so you can abstract away the behavior. So the goals actually help us decide which which parameters we need to represent and reason about, and which parameters we can ignore because we are reasoning about that goal and not other things. Because if abstractly, you can reason about everything. So the goals actually help us kind of reduce the possible ways we can reason about the ensembles.
Thank you.
Thank you very much. And last but not least, Lei Zhang, if you'd like to ask your question.
Right. So thanks a lot for this very, very interesting presentation. I have one question actually. So when we consider the collaboration between the robots, so I think the first very important thing is the trust, right? So did you ever consider how to build the trust between the robots? I'm not sure the architecture you are considering. Is it a centralized or distributed one? When we consider lots of robots in the future, they collaborate for one, task, on behalf of different parties. So how can we make sure they trust to each other? And if there are some malicious, robots, is there any consideration in your design here?
So in the examples I gave, we didn't explicitly address trust. One of the things, and that's kind of, we've been discussing a lot about it, is when we, in the last scenario, when we have groups of users, a group of users, and that needs to work with the robot. So the robot, if they try to build that kind of trust with those groups, one of the things is you trust people in your own group. So, and that kind of, there's this big question, how to make the robot share an identity, be part of the group. And for the moment, we don't know. But the direction is to make those robots part of those groups. There are markers that is like now we can observe whether the people kind of trust the robot or not, because the way they behave with them, but we don't know how to, intervene to build trust. We can only observe it, and that's kind of the question. So sorry, I can't answer. It is a difficult one.
No problem.
Thank you, Amel.
Thank you.
I'm conscious that we're coming up to the hour, which is the scheduled time for this talk, and I don't know whether we should or can overrun, and Radu can decide. I think he's nodding there, so I might take just one more question, a brief question by Nadine, and a quick answer by Amel.
Thank you, Amel, for the amazing talk, actually. So I'm also working in especially in domain system in the privacy domain from a contextual perspective. So my question is regarding your final bit that you presented, actually, when the social identities are not explicit, but you are trying to observe the markers in order to infer that kind of information. So in the picture, I can see that you are using a past incidents information. So I was like, so how do you gather that kind of information where the domain requires non-explicit information,
Yeah, so the way we've been doing it, and that kind of also basically Carlos and Anastasia as well, which is like a software engineer, researcher, and the social psychologist. So what they did is they have a corpus of past incidents, such as the London bombing, the 9/11, and there are videos, and there are text associated with it. And what they did is they took, I think the right term is utterances, so sentences, and they kind of label them whether they are more pro-self or pro-social. And the labeling is done by both of them. So kind of some reliability there. And then based on that, we gave it to a BERT transformer, like a machine learning algorithm, to extract or try to understand from those sentences whether it's more, classify it, whether it's a pro-self or pro-social behavior. So
is the corpus online, by the way?
Sorry?
Is the corpus online?
It's under review, so
Okay.
it will be released. Yeah.
Hopefully. Okay, thank you.
Thank
Yeah,
you.
thank you very much, Amel, and thank you for the very interesting questions. I think there's lots of opportunities for follow-up discussions, and Amel is a very friendly person who welcomes people to contact her by email and other forms to ask questions and to continue the discussion. I'd just like to close by thanking her again for a fascinating talk and invite you to join us for future meetings of the TAS Resilience node. So thank you very much, everyone, and thanks, Amel, again.